Okay, now let's talk about cross slip. We know slip is a mechanism for dislocation motion, and slip will move. Slip for the dislocation will move on the slip plane. And how about cross slip? And cross slip is a phenomenon or of deformation mechanisms that can occur in crystal when two or more slip planes with a common slip direction. So cross slip is related to slip, and this will occur when this conditions is satisfied. For example, let's have a look at the HCP crystal. We know that we have three special planes, right? Basal, pyramidal, and prismatic. We have three different planes. And then because HCP metals have less effective sleeve systems. So sometimes, although the basal planes is the preferred sleeve plane for the materials. However, the other sleeve system may initiate if necessary. So you see here we have this one. This is basal plane. And this basal plane and the prismatic. This one is prismatic plane. For both of these two slip planes, they have a common slip direction, this one. And also, this slip directions is the close pack directions. So it means that we know that for slip, dislocation must move on the slip plane. For example, on this plane and on this plane. And if we have a common slip directions, it means that the dislocation can move from this plane to this plane, right? Through these slip directions. And let's see the second picture. This is the cross slip in HCP metals. So first you see that this is the basal plane. Okay, this one is the basal plane, and we have a slip direction. This is the slip direction. So the crystal can deform like this. And then we also have another plane, prism, like this one. Okay, so this is the prismatic plane. And both of these two share with the same slip direction, right? So as a combination of these two, we may see the deformation mechanism like this one. It can deform like this in these directions. This could be part of the this is the basal plane deformations, and also if we go up like this one, this is the prismatic deformation. So we can see a jaw-like morphology of these locations. And how will we observe this jaw-like morphology? Because we will not observe the extra half plane or lattice distortion. We will just observe the dislocation line. So the dislocation line here, you will observe like this morphology. So this is what you will see. Okay, this is the cross slip phenomena in magnesium. So if you see the dislocation lines, not like this one, but like this one, it means that cross slip occurred in this material. And during cross slip, the dislocation will go from one slip plane to the other because they share with the same slip direction, right? And as we mentioned before, for screw dislocation, we first identify here, this is the screw dislocation line. And for the same Burgers vector, we observe that more than one slip plane can exist here. For example, for this plane A, we have a screw dislocation line here. For this plane B, we can have the same screw dislocation here. So when the Burgers vector in these directions, we know that the dislocation motions, okay, is perpendicular. So it can go to here and here, right? Both of these two are perpendicular relationship. However, for edge dislocation, if we define this edge dislocation line and the Burgers vector, there is only one plane here. This is the slip plane. Okay, so now we know that during the cross slip, dislocation will move from one to the other, and this dislocation must be screw dislocation because edge dislocation does not have the ability to go from one slip plane to the other slip plane. Okay, let's talk about slip line and slip bend. So first, when slip occurred in single crystal, okay, single crystal, and length one slip plane will be the primary one or the most favorable one. For example, like the typical structure here. So this is the slip plane here, right? And then we have numerous planes here. For example, let's draw a FCC here. We know that this is 001 plane, right? However, this is also 001 plane. We have numerous 001 plane here, but we should write it as 001 family of planes. So we have a large number of equivalent planes here. A list will form a lot of small steps. And for this line, we observe it as slip line, right? So basically, slip line is the location of slip plane. We have a lot of slip planes. And this a lot of small steps parallel to each other can contribute to the large plastic deformations. Okay, so with the continued extension of single crystal, that is, we use the stress with increasing stress length, we will see the number of this line increase and also the step here will increase too. So both of these two can cause the elongation increased. Okay. And how about slip bend? Actually, slip bend is a group of closely spaced slip line. In other words, slip line is smaller in dimension or in scale, and slip bend is larger. So if we use the SCM structure, we see the line like this one. We will call it slip bend. And actually, this slip bend is composed of a lot of slip lines. And here, slip bend can sometimes be complex because these lines are the are the slip plane, right? And if we have the cross slip to occurred, cross slip involve dislocation motion on the different slip planes. So for different slip plane, we may observe like this. So it will be more complex. Okay, let's talk about the different term. We call it double cross slip. So it's very important for you to identify slip, cross slip, and the double cross slip. At the beginning of this chapter, we learned about that we have two mechanisms for dislocation generations. The first one is Frank resource. The second one is dislocation nucleations. And most of the time, it will be heterogeneous dislocation nucleations. We must have the presence of the defects. And how about double cross slip? It's actually a mechanism, and it can be explained for the dislocation multiplications, just like the dislocation generation. So first, let's see this double cross-slip mechanism. Try to imagine we have a dislocation loop on this slip plane, and we call it primary slip plane because we now learn that for materials, it could have a lot of slip systems. So we can have the primary slip system and the secondary slip system and so on. So this one is the primary one. In other words, if we apply stress here, then the dislocations on this slip plane will move. So first, we have a dislocation loop here. Under the stress, it will enlarge. So we see here, it will enlarge, become bigger and bigger. And when this dislocation loop touch or meet the other plant, this is also a slip plant, but this is maybe a secondary slip plane, just it's not the primary slip plant. And because the dislocation loop is become bigger and bigger, and only, as we learned previously, only the screw dislocation can move from one slip plane to the other slip planes. So the screw dislocation segment will go up on this plane. So we call this cross slip, right? Go from one slip plane to the other slip planes with the same what? With the same slip directions. And then let's see, because it's this slip planes also the screw dislocation can move on it. So it will continually go up. And eventually when it go to a parallel primary slip planes. This one, A and B, they are the same slip planes, just equivalent. For example, as we talked about in previous slide, it could be, for example, 0001 for HCP and 0001 for HCP. Okay? Draw it. 0001 for this one. 0001 for this one. Okay. And when, okay, we must first identify here. This CD, DC, H, DC and the AB, they must be H. Okay, they must be H. Because we identify a dislocation line here, we also identify the Burgers vector here. So this one, it must be the H dislocation, not the screw dislocations. And then, because these two are H dislocations, and This is not the slip plane for the edge dislocation. The slip planes, the primary slip plane for the edge dislocation is this one. So edge dislocation can move on A and B, not on this one, C. So these two lines will be fixed. They cannot move under the stress. However, when you go up here, these 2 points cannot move. However, the screw sections, the screw segment can move. So it will go like this. It's similar, right? This is the mechanism for Frank Reed source. So when dislocation loop move back to the original slip plane, but a parallel one, it will act like a Frank Reed source. Okay, so this line, screw segment, act as Frank Reed source. So we learned at the beginning of this chapter, the Frank Reed source can produce more dislocations. However, Frank Reed source combined with this double cross slip is actually much more probable than just the Frank Reed source. Okay, so when we are going to talk about the dislocation generations, you may say that the Frank Reed source with double cross slip. This is first mechanism, and the second mechanism is heterogeneous dislocation nucleation. And let's give some review of the plastic deformations. I think all of you have learned it from the material science and engineering course. So for plastic deformations, it means that we use the increasing stress. So we will have the elongation, we will have the strength. When the strength is too large, and then the strength will become permanent and cannot be recovered. So this process, this deformation process is irreversible. And on an atomic scale, you will figure out that it involves the breaking bonds and the reforming of the bonds. Okay, just like first we have a perfect crystal with a slip plane here. And then we have edge dislocation with extra half planes. And after it moves, sorry, not this direction. Okay, it's okay. After it moves like less directions, the edge dislocation move. So eventually, we see that both of these two parts are perfect crystal, but we see a step here. This is the dislocation motion and the plastic deformation relationship. And most structure, okay, this is for material design. Most structure are designed to ensure that only elastic deformation can occur under a stress is applied. However, we must know that when plastic deformation will occur or not. So the boundary between elastic deformation and plastic deformation is what we call yielding, or the proportional limit. Okay, proportional limit. And let's use this figure to talk about the yielding, yield strength, and proportional limits. So for general materials, yielding will occur for these two conditions. First, when the strength is greater than the proportional limits, this point. So when the strength go here and exceeded a strength value here, then it will be, sorry, not this. we will call it as the yielding. So this is the yield point. However, this is the strict definition, but this point is hard, difficult to measure. So in general, we will use this method. This is what we call 0.2% offset. So the method is we first go from 0 to 0.2%, that is 0.002, and then draw a parallel line to this one. Then we meet the curve. This point, we call it yield point. Then we define it that after this point, we have plastic deformation plus elastic deformation. Before this point, we have elastic deformation. However, we know that the actual point is this one, proportional limit, but this point is actually very close to this one. Okay, so try to know the difference between proportional limit and the yield point. And how about yield strength? Yield strength is the stress at strain value equals to this one. And the meaning is the materials resistant to plastic deformation. So we draw here, go for 0.02, draw a parallel line, and for this point, this is yield strength. And for some materials, like steels, we will have upper yield point and lower yield point. And based on the definitions, we will use lower yield point as the yield strength. Okay, and let's talk about some fact for elastic and plastic deformation. So for elastic deformation, before the proportional limit, it will be elastic deformation. In other words, you load with the stress and then release the load. It will go back to the original one. And the slope, we call it modulus of elasticity or elastic modulus. And then for plastic deformations, when you exit this point, this is yield point, then after that we will experience plastic deformation. It is permanent and irreversible. And how to see it for permanent and irreversible? For example, you go here and then you release the stress, let it unload. So you go back, but it will not go back to the same point, right? We have distance here. So this one is what we call the irreversible plastic deformations. But it still go back a little bit. So this one is called the elastic strain recovery. So you need to know that when the strain is larger than the yield point, we will have plastic deformations, but we still have a certain amount of elastic deformation. So that's what we will set. For this point, we have elastic deformation. After this point, we have elastic plus plastic deformations. And this step is for elastic deformation recovery. And you see here, it's very interesting. After this is the first tensile test, right? Then we conduct it again, reapply the load. Then based on the definitions, we will get a yield strength here. And we find out the yield strength, initial one, and the yield strength after plastic deformation. This one, after plastic deformation, the yield strength will increase. So this is the important concept, strain hardening. It means that we apply stress or strain to the material. After that, the materials will experience hardening. And for the concept of true stress and true strain, you have the equation here for engineering stress, true stress, engineering strain, and true strain. I think you already learned about this. So this is just to let you know that the difference between engineering stress and the true stress. And we have an equation to convert between these two. Okay, convert between these two. And the important part is, why do we have the true stress and true strain? Why don't we just use the engineering stress and engineering strain? This is because we will have a phenomenon we call necking. And before necking and after necking, the phenomenon would be different. And necking is about after one point, then we will have the stress concentration at the necking regions. So before necking, it's uniform deformations. And when we increase the stress, sorry, this is the force. When we increase the force, the stress will increase. This is the sigma without T is the engineering stress. And also true stress will increase as well. However, after necking, it's the non-uniform deformations. And the deformation will focus on the necking regions. So the force will decrease. The engineering stress will decrease. However, the true stress will increase. Let's have a look at these two equations. This is for engineering stress. So after necking, force decreased. And A0 is the initial cross sections. This is the same. So this one will decrease. And how about the true stress? Force here decrease. However, due to the necking is in at the center regions. So the cross-sectional area will decrease. However, it decreases more compared to the decrease in force. So we will see that the true stress actually will increase. So that's why we need to have the true stress and true strain. Otherwise, if you just use engineering stress and engineering strain, you will figure out that, okay, after necking, the stress will decrease, so the material strength will decrease. And actually, this is not true. During the process, the strength hardening will occur and the material strength will increase all the time. And let's see this, the corrected true stress and true strain curve. Because of this complex necking behavior, so we use a corrective equation of this one. Okay, and N is the strain hardening exponent. It ranges from 0 to 1. So with a larger N, the curve looks like this one. With a smaller N, the curve looks like this one. So with a higher strain hardening exponent, the strain hardening effect will be more significant, okay, compared to the one with a small N. And if we do not use the correction, you just use the equations, the true stress will go to this curve. But actually, it should be like this one, because after necking, it's very complex. We should use these equations. However, if we just use the engineering stress strain curve, this is an entirely different curve. Okay, And after we learn about necking and the true stress and true strength, we can talk about this consider criterion. This is equations, and we will not derive it here. So for the necking behavior, the slope of the true stress and true strain curve, okay, true stress and true strain curve, like this one, right? And we have a necking point. We have a necking point. So for the necking point, we have a slope here. And this slope equal to the true stress. Okay, so this is the considered criterion. And let's talk about walk hardening or cold walking. First, let's identify this term, flow stress. We add a flow here. The flow stress is the stress at which metal will flow. Okay, so it's just similar concept as the dislocation structure, because the dislocation will assist plastic deformation. So actually, the stress here, you can also call it as flow stress. And now let's talk about the strengthening mechanisms. So generally we have four: ground boundary strengthening, solid solution strengthening, strain hardening or walk hardening, and precipitation hardening. And here, let's talk about strain hardening. Okay, I think we have talked about the right-hand figure before. First, we have initial yield strength, and after that, we applied plastic deformation here. This is the amount of plastic deformations. And then we reapply the load, and we can observe that the yield strength after elastic deformations, it becomes higher. So this is the strain hardening. In other words, you apply stress and strain to the material, then it becomes harder and harder. And when the ductile material is deformed, it becomes harder. This is the meaning of work hardening and strain hardening. When it is deformed, it's strained. And after the strain hardening, the yield strength and the tensile strength will increase. However, the ductility will decrease, and you can see here. This is the trend of yield strength and percent core work. Let's talk about it here. So with increasing percent core work, YS and TS will increase, but the ductility will decrease. And how about the percent core work? How to identify the deformation amount? So we use these equations, percent core work, to express the plastic deformation degree. And actually, these equations you see here is A0 minus AD over A0. It's actually the same equation for ductility. But for ductility, we have two expressions. This is percent RA, percent reduction in area. We also have percent EL, percent elongations. And for percent RA is the reduction in area. So the area reduction and convert it to the percentage. We call it percent cold work. And why we call it cold work is because the temperature during plastic deformation is relatively low compared to the melting point. So cold work refers to the melting point if it's relatively low. So with increasing cold work amount, it means that the materials experience severe plastic deformations. and it will cause the decrease in dislocation motions and then the increase in the strength. So in the next slide, let's talk about the decrease in dislocation motion and the mechanism. Okay, so here let's talk about the percent core work. So based on these equations, if you see that a material with 0% core work, it means that, for example, the area go from 100 to 100. So there's no change. And 4% core work means that 100 to 96. So this is very small. So this is just to let you know that 10% core work is small. It goes from 100 to 90. And 90% core work is large. It goes from 100 to 10. Okay, so you must know that because for some materials, it will let you know the percent core work of these materials. You must know that 90% is very high and 10% is very low. And now let's talk about the mechanism for work hardening or strength hardening. So as we learned before, we know that if we have dislocations, then dislocation would have a strength field. And the strength field between two dislocations, for example, you see here, two positive edge, then that would interact with each other. And if it looked like this two edge dislocations with the same sign, then that would have a repulsion force. So first, let's begin with the dislocation densities. When the materials experience plastic deformation, first you need to know that the dislocation density will increase due to plastic deformations. This is because when the plastic deformation occurred, the existing dislocations, the original dislocations, is not enough to induce the large plastic deformation. So dislocations must be generated during plastic deformation. And the mechanisms, we can describe it by the frag resource or the dislocation nucleation mechanisms. And when the dislocation density increased for a certain area, the average dislocation distance will decrease. So you will see more often for these conditions. And it will restrict dislocation motion, right? Because it will experience repulsion to each other due to the dislocation interactions. Okay, so, and also when the dislocation density increased, it will increase the probability of dislocation intersects, as we learned in the first chapter. So it will make the materials harder because dislocation will be hindered for the motions. And it's worth mentioning that the effects we talk about here for the strength hardening, it can be removed by annealing. So for the next two chapters, we'll talk about annealing. So when we put the material, the metals in an oven, then and at a high temperature, then the recovery, recrystallization, or grain growth will occur. And then this effect will be removed. Okay. And also for the grain bonder strengthening, it can be removed as well. However, for solid solution strengthening, if you do the annealing treatment, the solute atoms will still remain in the material. So the solid solution strengthening cannot be removed by the annealing process. Okay, and now let's have this PBLO question time. First, this is about an indentation reminder in hardness test. And the question is, when we make a hardness measurement, for example, like Vickers micro hardness or Rockwell, and then what will be the effect of making indentation very close to a pre-existing one? For example, this is an area of what you see in the optical microscope, OM. Then you made an indentation here. This is the first one. And then when you made a second one, for example, you made it here. Then they have a distance away, very far, they will be fine. However, if you made it here, very close to the pre-existing one, what will happen? And here are some background uh, required for your thinking. So first, hardness is a measure of material surface resistance to local plastic deformations. So the mechanism is we use an indenter, usually diamond. We use this indenter to put on the sample surface with different load or force for a certain time. And then we use a diamond because diamond is very hard, and then we use a force would indent on the surface, so we will see a mark like this. Okay, then we calculate the mark dimension. Try to imagine that if you use a larger load, then you can expect that the dimension of this mark would be larger in that dimensions. So we now know that hardness is about the surface resistance to plastic deformation, and what will happen if we do it for the second time and length very close to the first time. Okay, I will give you 5 minutes to think about it. I think this is a very good time for you to learn how to solve the question, how to solve the problem by the basic. This is not just about me giving lecture to you, because it's just like I tell you the answers, and now you can try to find out the answer yourself by this background. Okay, I will give you 5 minutes. Okay, I think it's uh, about time. So for the indentations, you must first know that hardiness is a measure of the local plastic deformation. In other words, when you put an indenter onto the sample surface and then you use the load, it means that you applied load to the surface to create, to produce plastic deformation. So after the plastic deformation, you will see a mark here. So this mark is a result of plastic deformations. Okay, so mark equals to result of plastic deformation. And the question here is, what will be the effect of making an indentation, making a mark very close to the pre-existing one? So for the first one, this is a result of plastic deformation, and the second one very close to it. Now we know that when we applied load to material and caused the plastic deformation, the material will become harder, right? Due to the plastic deformation. This is the mechanism of strain hardening. With the strain, the materials will become hardening. So hardening is due to it has a strain field. And when the indentation make very close to it, the strain field will affect the result here. So for example, for the first one, you get 100 HV. This is a unit for hardness, viscous hardness. First one, you get this one. Then the first one will be higher than 100 HV, maybe 112 HV, because the region near the first one has been hardened by strain hardening mechanism. So this is a reminder for you to let you know that when you are doing hardness measurement, you cannot put the indenter very close to the pre-existing one, because the value you get will not be the exact values as it should be. Okay, so this is a very important reminder. Otherwise, you will get the wrong answer, the wrong data. Okay, we have another one, another indentation reminder for the hardness test. Okay, so again, when making hardness measurements, what will be the effect of making an indentation with a very large load? And then the material is a thin film with a very thin thickness. Okay, and also we have a background for you for the thinking. The first one, hardness is as we said, as a measure of a material surface resistant to local plastic deformation. The second one, for a thin film material, we usually fabricate it onto a substrate. For example, we first use silicon substrate, and then we deposit a material here. For example, just an example, gold. Okay, and gold is very thin. For example, 100 nanometer. Okay, so this is what we call the substrate. Okay, and this is our thin film. If you made an indentation with a very large load in a very thin film, what will happen? Okay, I think we have enough hints for you. And also, let's take 5 minutes for you to think about it. Okay, I think it's about time. Actually, for this question, it's not that hard because once I draw this structure, you will know that when you use an load, because from the top view, okay, from the top view, we made indentation, right? And from the cross-sectional view, this is cross-section. The indentation look like this. So when you do a small one, this is the mark. And the large ones, I think you will know that when you use a very large load, let's make it even more. For example, like this one. This indentation is very, very large. It even touched the silicon. So what we want to measure is the hardness of gold, but you measure the hardness of gold and silicon together. So of course, the results would not be correct, right? So for the measurement, hardness measurement of a thin film materials, usually we need to control the size of the indentation. And then we must control the size of this indentation of less than 10% of the fin thickness. For example, this fin thickness is 100 nanometer. So for the depth, okay, the depth of this indentations, it must be smaller than 10 millimeters. Otherwise, the results you get will be affected by the substrate. Okay, it will be affected by the substrate. This is what we call the substrate effect. And if you have a thin film materials, you need to pay attention to this substrate effect. And also the previous one, you cannot make it too close to the pre-existing one. Okay? And now let's see the relationship between dislocations and stress. So this is the typical stress strain curve, right? With different strains, we choose different region here. So different points are tested for the dislocation density. As we learned before, we know that we applied stress to materials. Then plastic deformation will occur. Then the dislocation density will increase. And now let's see the results, experimental results. Here, this one is the dislocation density. This is the stress, okay, the stress here. And then you see here, for different dislocation density, then you will find out that they have different stress, and it has a correlation of this one. This is the sigma equals to sigma 0 plus k rho half, okay? And then this is actually, you see here, with different grain size, it match these equations. Okay, this is the equation for work hardening, and rho is the dislocation density. So when the dislocation density increased, you can expect that the strength of material will increase. And also this is the stress. You can also convert it to shear stress, because shear stress is the stress for dislocation motions. So tau equals to tau 0 plus k rho square root of rho. Okay. And then let's talk about a well-known Taylor's equations. Taylor's equation is an equation to describe the relationship between flow stress and dislocation density. So also it's about stress. And the basic assumption is all dislocations move on parallel slip planes, and the dislocations are parallel to each other. So the first one is we will assume a primary slip plane, right? So they will be parallel to each other. And the second assumption is the dislocations are parallel to each other. This will avoid the complex dislocation intersection. And based on these results, you can guess that we have tau. Tau is resolved shear stress. This is for the force stress. And alpha for the constant. And mu for the shear modulus. B for Berger's factor. Rho for dislocation density. Actually, this one is a very classic one. Taylor's equation. And then we also have Orwell equations. It's to describe the relationship between the strain rates and the dislocation velocity. So you see here the epsilon dot tensile strain rate and gamma dot shear strain rate, dislocation density, Berger's factor, and average dislocation density. Okay, and let's talk about some supplementary information for dislocation in ceramic. As we learned, this is the dislocation in metals, right? And these ones are dislocations in ceramics. So we must know that perfect materials don't exist. Perfect means perfect order of atomic arrangement. So definitely you will have defects. And dislocation is one of the defects. This is the linear defect. So dislocation will exist. And perfect material doesn't exist. Dislocation exists. So dislocation exists in ceramic. And how about the dislocation motion in ceramic? So for the ceramic material, actually we have two types. One is covalent bond, the other is ionic bond. Okay, so for ionic bond, we have cation, and cation and anion. Okay, cation and anion. Okay, and here for covalent bond, it could be, for example, like copper bond, and silicon. Okay, and it will be hard for this because for the covalent bond and ionic bond, they are very strong, very strong. So when the dislocation must move in the materials, then we will have the breaking bond and reforming of the bond. So for the dislocation motions in ceramic, it will be harder compared to the one in the metals. Okay, I think we have finished that for the chapter 2. And here are some important summaries. So first, this is an important concept. We apply external stress and it will cause resolved shear stress. The shear stress will cause the dislocation motions. And when dislocation move, it will cause the shear strains. And meanwhile, we must have new dislocations for the plastic deformation. So the dislocation motion would be the pre-existing one and the newly formed one. Okay, and we have two types of dislocation generation mechanism. One is fragment source, the other is a dislocation generation nucleations. For the fragment source, usually we will say that it will be combined with the double cross slip. Okay, use double cross slip. We will talk about later. And for the dislocation generation, nucleations, we have homogeneous and heterogeneous. And usually this one will happen. And for the materials, the plastic deformation occurred, and 5% of the deformation energy will be stored in the material. We call it stored energy. And the dislocations with the same signs will experience repulsions. With opposite signs, experience attraction and annihilation. So for the repulsions, this is for strength hardening. And for this one, is for recovery. Okay, and then we have three types of crystal deformation: simple shear, band gliding, and rotation slip. Okay, and you can check the band gliding and rotation slip here. And for the slip system, we have slip plane and slip directions. So they are the preferred plane or preferred directions, and it must be the highest planes and highest linear densities for the structure. And the slip direction must be on the slip planes. So the slip directions and the normal direction of slip planes, they have a perpendicular relationship. So the inner products will equals to 0. And then we have a term, resolved shear stress and critical resolved shear stress. Make sure that you understand the definition. And then here we list the slip system for you for the FCC, PCC, and the FCP. Okay, we have easy glide, also check the definition. And here we have cross slip and double cross slip. These two are different. For cross slip, it's about that dislocation move from one slip plane to another slip plane because they share the same slip directions. This can only occur for screw dislocation. It's very important. And for double cross slip, it's a mechanism to explain dislocation multiplications. Okay, we usually combine this mechanism for the frag resource. And for the work hardening or strength hardening, the material will become stronger, but the ductility will decrease. And the mechanism is, okay, this is also very important. You need to know the sequence here. First, when you apply stress to materials, dislocation density will increase. So the average dislocation distance will decrease. Then they will experience dislocation repulsions and also the dislocation intersection. So it will make it hard to move. When the dislocations are hard to move, the materials will become stronger and stronger. And here are two useful equations for you. Okay, I think that's all for the chapter 2. Thank you for your attention.